start recording. So, welcome back, everyone. I hope that you had a great weekend. So, just a few admin stuff that we need to get out of the way. We are about 140 registered students for this module, and only 97 has filled in the Google Sheet with your information so I can get a WhatsApp group started for this class as well. So just ask to please remind everyone to fill in the Google Sheet and just remind the rest of your class friends that to fill in the sheet as well. I will answer the questions on Discord and in the Google Doc tonight and tomorrow. And before we start the session, does anyone have questions? Anything you want to discuss? Anything you want to tell me about? Yes, you can ask a question. Yes, Miss Corbe, so you raised your hand.
Hi, Professor. So I had like a beginner's thing, so I wasn't actually in the lecture. I only watched it after Tuesday's lecture. I only watched it afterwards. And I have a question. Can you please clarify the meaning of planets that aren't in our, like, what makes them not a part of our solar system? Like, I'm not sure what the exact phrase was. Do you know what I'm
Okay,
talking
so
about?
yes, you're talking about exoplanets.
Yes.
So exoplanets, so we're going to discuss that in later chapters, but to give you a explanation now, just open up the whiteboard. So in our normal solar system, we would have our host star. In this case, in our solar system, it is the sun. Then around the sun, we would have different planets, and these planets would all orbit around the host star, or sun in our case. So everything orbiting around our own sun is part of our solar system. But different stars have their own planets orbiting them. So when we're speaking about our own solar system, it's a planet, we refer to it as a planet in our solar system. If it is around a different star, then we call it the exoplanet because it is external to our own solar system, if that answers your question. So question, are there any tutorials or pracs for this module? No, there are no tutorials or pracs for this module. We can have a semester test, one big assignment, and a few pop quizzes. It's a pleasure. Anything else you guys want to know? Anything else I can help you with? No quizzes this week. I will let you know when our first quiz will be and on what it will be. It's a pleasure, Miss Corby. Another question. Can I explain what dark matter is? That is a really interesting question. If we look at our known universe, we can determine what is the material that everything exists of. What are their composition? If you go to the subatomic level, we can break it up into protons, neurons, electrons. We can go even smaller and go to quarks. But if we look at the known universe, 90% of the known universe, we don't know what it consists of. We know it's there, but we can't prove it, and that we refer to as dark matter, if that answers your question. But yes, I see your hand is raised. You're more than welcome to answer your question.
Hello, say, can you hear me?
Can you repeat that? Your mic was just really soft.
Oh, can you hear me, say?
Yes, I can hear you.
Good evening. So I was just wondering, Mercury is the closest planet to the sun, right? Is that so?
Yes,
Okay, so I was just wondering, like, isn't it supposed to be like the hottest planet ever? Like, when we are talking like temperature wise, isn't it supposed to be like the hottest planet, like among all the planets?
that is where it's interesting. Mercury is one of the hottest planets and one of the coldest planets at the same time.
Exactly.
Be-
That's what I wanted
because
to ask. Like,
Mercury, because Mercury is
okay,
so
go on.
close to the sun, the part of the surface that's pointing towards the sun will be extremely, extremely hot. But the other side of the planet, that's in the shadow of the planet, will be extremely cold.
Oh, okay. Okay, so that's
But
the reason why it's one of the coldest planets.
so one of the hottest and one of the coldest.
Oh, okay, okay, sure. Thank you, sir.
It's a pleasure. We will discuss that in later chapters as well. So
Okay.
let me share tonight's slides. Can everyone see the slides? Okay, cool. So before we begin, has any one of you learned something new in science the last week that you'd like to want to share with the class? So do we need to follow the textbook at the same time as the lecture? No, you don't have to follow the textbook during the lecture. My slides is just summarized sections of the textbook. But if you want more in-depth knowledge and more finer details, then you can refer back to the textbook. So one thing in science that we learned last week is the Large Hadron Collider of CERN has discovered 4 new particles. Yes, it's the Mars orbiter. So more precisely, Perseverance rover that landed. And yes, there's a big asteroid that missed Earth slightly. So the orbit of the path of the asteroid went, if you put it the distance in perspective, the moon is about 380,000 kilometers away. The asteroid passed between the Earth and the moon. So, where do you read up on science news? So, on social media, there are a few nice science pages that you can follow, and also there's a few cool sites. I know NASA's website is great. There's heavensabove.com and a few other places as well. Pleasure. So, in tonight's lecture, we're going to look at chapter 2 and chapter 3 of the textbook. So in this chapter, so another comment, so I read this week that it was first suggested in 1690 that Jupiter might not be a solid planet, but made of gas. So Giovanni Cassini noted that a planet was rotating at different rates depending on its latitude. Yes, and we are going to learn more of his work in later chapters as well. That's a cool website. Thank you for sharing. So in tonight's lecture, we're going to ask a few questions. Why do we study astronomy? What is a scientific method? The user's guide to the sky and its motions, cycles of the sun and moon, cycles of the sun, motions of planets, astronomical influences on Earth's climate, the changeable moon, the motions of the moon, the cycle of moon phases, lunar eclipses and solar eclipses. So we're going to start off with a quote of Neil deGrasse Tyson. Are you all familiar with Neil deGrasse Tyson? Awesome. So the good thing about science is that it is true whether or not you believe in it. So see another Star Talk fan. So I'm going to like to ask you guys, why do we study astronomy? Curiosity, it's cool. What else? Human nature sounds fancy. You guys are, now what's out, eh? So you all are touching on really good points. But if we can break it down a little bit further, is to answer more deeply questions of what are we and how do we know. So, out of astronomy, if you ask the general public, what do we learn of astronomy? Why do we do astronomy? It is because us as humans are a very curious species. We want to know what is out there, how stuff works, how things are made, how everything fits together. So if you think of astronomy, how does it affect the general public every day? So how does it affect the general public every day? It affects the public directly and indirectly. So directly is the technology that's developed for astronomy. For example, take the Mars Reconnaissance Orbiter, the cameras that was developed for the orbiter, specialized cameras, but now that technology has ciphered into everyday use in our fancy cameras that we can buy. And the other reason is, again, to ask questions. Who are we? What are we? How does everything fit together in our universe? So, comment. I watch a lot of TV shows that talk about dark matter, multiverse theory, so I want to know about those stuff and more. So, in the last chapter of this model, we will touch more on those subjects. So the question, what are we, is the first organizing theme of this course. Astronomy is important to you because it will tell you what you are. Notice that the question is not who are we. If you want to know who we are, you might want to talk to a psychologist, sociologist, theologian, pathologist, artist, or poet. What are we is a fundamental different question. As you study astronomy, you will learn how you fit into the history of the universe. You will learn that the atom in your body had a first birthday in the Big Bang and when the universe began. Those atoms have been cooked and remade inside generations of stars, and now, after billions of years, they are inside you. So where will be another 10 billion years? This is a story everyone should know, and astronomy is the only course on campus that can tell you that story. Can everybody hear me loudly? Okay, please let me know if there's any problems, if you can't hear me clearly. I know the last week Blackboard had a little bit of difficulties with a few modules. So if anything doesn't work or seem to be fine, just please let me know ASAP. So talking about the slide, have you ever thought where does material, where everything around us comes from? Have you guys ever thought where heavy metals come from? And not Metallica, but have you ever thought where does gold come from? Where does silver come from? Where does nickel comes from? Bingo, yes, from supernova and hypernova explosions, so from space. So if you think about the calcium in your bones is not a naturally occurring element on Earth. The only place where these heavier elements are formed are in giant stars that went supernova and it spilled its guts throughout the universe, and that got caught up in the formation of new stars, new planets, and eventually where we are today. So that is where the famous Carl Sagan said we are all made of star stuff. So the question, how do we know, is the second organizing theme of this course. It's a question you should ask yourself whenever you encounter statements made by so-called experts in any field. Should you swallow a diet supplement recommended by a TV star? Should you vote for a candidate who warns of climate crisis? To understand the world around you and to make wise decisions for yourself, your family, and for your nation, you need to understand how science works. So do you consider the Big Bang the origin or half-life counting? I consider the Big Bang the origin of everything. So, how do scientists learn about nature? So just for this interesting scientist, an expert in science who does precision guesswork based upon unreliable data from questionable sources, who organizes the results in ways most people cannot understand. So, let's talk about this a little bit. How do scientists actually learn about nature? Have you guys ever thought about that? Yes, so they observe it. There's the scientific method, observations. Yes, both of those are good points. They experiment, they test. Mathematical modeling, yes. So hypotheses, yes. So we're going to discuss now how the scientific method works. We need a scientific method to determine how things work and to learn about certain objects, certain features, certain phenomena. So do we have a planetarium here at our university? No, unfortunately not. The closest planetarium is at Wits University. There are not many planetariums in the country. I think there's 3 planetariums in the country. One is at Wits, one is in Cape Town, and there's one on the northeast coast somewhere, I think in Port Elizabeth, around about there. So you all have probably heard several times during your education about the scientific method as the process by which scientists form hypotheses and test them against evidence gathered by experiments and observations. Scientists try to form hypotheses that explain how nature works. If a hypothesis is contradicted by evidence from experiments or observations, it must be revised or discarded. If a hypothesis is confirmed, it still must be tested further. In that way, very general way, the scientific method is a way of testing and refining ideas to better describe how nature works. So before going on, have any one of you used the scientific method before? Good. So I see here a comment from Miss Niemand. I have a mathematical modeling as a module, and my prof said the hypothesis is always wrong. So that is something very interesting. And I will agree with that statement as well. So when we do the scientific method, what we usually do is we observe what's going on around us. And by observations, we then try to predict what it will do, because if we can predict what it will do and how it operates, then we can understand it. So from our observations, we create a mathematical model. Like I said in last week's lecture, the language the universe speaks is mathematics. So I don't want you guys, I don't want you to think about mathematics as mathematics, but mathematics as a language, the language that the universe speaks. So if we construct a mathematical model of something, that means we are trying to understand it. And usually our mathematical model can prove or disprove our hypothesis. So we can adjust our hypotheses based on our mathematical model that we created. From a physics standpoint, to prove these theories, we need sound mathematical models. From an engineering point of view, if you want to design something new, create something new, you first have to do a mathematical model. If your mathematical model is working, then you can create a design of the thing you are trying to create. So, are you guys, so what are most of the most famous constellations that we see in the night sky? Yes, Orion, my favorite constellation. Southern Cross, Scorpion, Big Dipper. Yes. So, all around the world, ancient cultures celebrated heroes, gods, and mythical beasts by giving their names to groups of stars called constellations. The constellations simply celebrate the most important mythical figures in each culture. The oldest constellation named in Western cultures originated in Assyria over 3,000 years ago, and others were added later by Babylonian and Greek astronomers. Of these ancient constellations, 48 are still in use. Originally, constellations were only loosely defined groupings of stars. Many of the fainter stars were not included in any constellation, and the stars of the southern sky, not visible to the ancient astronomers of northern latitudes, were not grouped into constellations. So constellation boundaries, when they were defined at all, were only approximate to a star like Alpheratz could be thought as part of Pegasus or part of Andromeda. To correct these gaps and ambiguities, astronomers have added 40 modern constellations, and in 1928, International Astronomical Union established 88 official constellations with clearly defined boundaries. Ah, see, I love the story of Orion and Scorpion. So I'm going to put you a bit in a hot seat and ask, would you like to tell the story to the class? No, that's fine, and we'll continue on. So, in addition to the 88 official constellations, the sky contains a number of less formally defined groupings called asterisms. The Big Dipper, for example, is a well-known asterism that is part of the constellation Ursa Major, or in better known terms, the Great Bear. Are you willing to tell the story by unmuting and talking over the mic? Okay, that's fair enough. So I feel that many of the constellations are a stretch of imagination. I'm not sure if just me, but I can never make any of them out. That's true. So a lot of those constellations are a stretch of imagination. Some constellations are clearer than others. So some of the two constellations that stands out the best for me is Orion and Scorpio. So, question, how do people see patterns in randomness? So that's one thing us humans like to see in things is patterns. We like to interpret patterns and to find patterns everywhere we see. So that's why I've ever thought about a spiral. Let me see. So, spiral, if you do the maps behind it, that's basically the Fibonacci sequence. So everywhere we like to see patterns. So in a night sky, you can also make patterns. The same principle you can argue as when you look at clouds and you can see the clouds making different forms. That is still looking at patterns. So pattern recognition is a very important aspect of humans. So a few comments. Yes, after class I will upload the slides immediately. So all constellations observable everywhere on Earth, or some are restricted to certain places. So usually constellations are restricted to northern hemisphere and southern hemisphere. So some constellations that are more on the equator, you can see from both northern and southern hemispheres, but some constellations like the Big Dipper we can only see from the northern hemisphere, and the Southern Cross we can only see from the southern hemisphere. So how did I assign months to these groupings? We will come to that. Thank you for providing us the story. So when we look at star names, that's also an interesting aspect, is how do the stars get their names? So in addition to naming groups of stars, ancient astronomers gave names to the brightest individual stars. Modern astronomers still use many of those ancient names. Although the constellation names came from Greek translated into Latin, the language of science until the 19th century, so most star names from the ancient Arabic, much altered the passing centuries. Naming individual stars is not very helpful because you can see thousands of them. How many names could you remember? Also, a simple name gives you no clue to the location of the star in the sky or to its brightness. A more useful way to identify stars is to assign letters to the bright stars in a constellation in approximate order of brightness. Astronomers use the Greek alphabet for this purpose. Thus, the brightest star in a constellation is usually designated Alpha, the second brightest Beta, and so on. Often the name of the Greek letter is spelled out as in alpha, but sometimes an actual Greek letter is used, especially in charts. So, do you guys guess where this is leading up to? Not star charts, but how do we define brightness of stars? So to identify a star by its Greek designation, you would give the Greek letter followed by the possessive form of the constellation name. For example, the brightest star in a constellation Canis Major is Alpha Canis Majoris, which can be written as Canis Majoris. This both identifies the star and a constellation and gives a clue to the relative brightness of the star. Compare this with the ancient name for the star, such as Sirius, which does not give you any information about its properties. Interesting, Sirius is the brightest star in the southern hemisphere that we can watch. So, are constellations in the same plane as the Milky Way rotation? Yes, it is. So, almost lumens, but in astronomy we work with a different definition of brightness that we're going to come to in a few slides. And then surely the constellations we see today one day won't exist. Yes, they won't exist. So why we are learning about constellations now is it forms part of the history of astronomy. As we learned in last week's lecture, astronomy is a observational science and a historical science. So to give you all the knowledge, we are starting from the history and making progress to where we are today. So some of the stars we see don't exist anymore. How do we determine which ones? We will come to that as well. And then in this case, Sirius is a very bright star. We will come to the classification in a couple of slides as well. So in this picture, this comes out of our textbooks. We can see Orion in a visual image, but Alpha Uranus is also known as Betelgeuse, and Beta Uranus is also known as Rigel. So Betelgeuse is a giant red star or supergiant, and it is a lot bigger than our own sun. I will also post a video. That's usually when I will show video in class of the different sizes of stars. But I will, unfortunately, that doesn't work over Blackboard. So after class, I will post a link to that video. So here we can see star names. Sirius, the brightest star in the southern hemisphere. We can usually see it better during winter months, and we can define it as Alpha Canis Majoris. Then we can go through Betelgeuse, Rigel, Aldebaran, Polaris, Vega, Spica, and continue on. So unfortunately, I didn't have a look at Vsauce yet, but I will. Last week ran away from me. So, star brightness. So astronomers usually describe the brightness of stars using the magnitude scale, a system that was first appeared in writing of Claudius Ptolemaeus, also known as Plotinus, pronounced as You can see it here, about 140, in a year 140. So the system probably originated even earlier, and most astronomers attribute to the Greek astronomer Hipparchus, about to the year 190 to 120. Hipparchus compiled the first known star catalogue, and he may have used the magnitude system in that catalogue. Almost 300 years later, Ptolemy used the magnitude system in his own catalogue. Successive generations of astronomers have continued to use the system. So do we have to know all the star names? No, you don't have to use all the star names. So how do we study for this module? So once you've done a quiz or two, you will know how to study for this module. But most likely, best is no definitions. And if we do an example or two, how to do the calculations in those examples, it's really straightforward, easy calculations. Then again, definitions and facts. So here we can see how star brightness works with the apparent magnitude scale. So the early astronomers divided the stars into 6 classes. The brightest were called first magnitude stars, and those that were fainter, second magnitude, and so on. The scale continued down to 6 magnitude stars, the faintest visible to human eye, so the human eye can only pick up or look at magnitude 6. So, but then we decided, okay, we have better instruments, we have closer objects such as the sun, the full moon, Venus, other planets. So then the magnitude scale was shifted into the negative side of things to say, so if it's negative, it's more bright, and if it's positive, it's less bright. So here we can see the naked eye can spot magnitude 6. Hubble Space Telescope's limit is 27. And the sun is sitting at minus 26. So this gives a less a way to classify the brightness of stars. So how much brightness can the human eye take? That is actually a good question. If we go at super brightness, the sun is sitting at minus 26. That can even go upwards, but the faintest we can see of the human eye is magnitude 6. Do you guys have any questions so far? Okay, so let's continue on. So what is magnitude? We're going to come to that in the next slide. So where on the scale would be bright enough to blind you? I'm not quite sure, but I know if you look at the sun for a prolonged time, that can blind you. So I would say probably from minus 25 and upwards. So what does the MV stand for? That is apparent magnitude. So does the Hubble convert the magnitude to magnitude usable by humans? No. So basically what Hubble does is, it's cameras, not cameras, it's lenses it has, is sensitive enough to pick up stars from 6 magnitude all the way up to 27 magnitude. And it is exposed for a long time. So in math terms, we call it integration time. And then that's converted to an image, and we use the image. Yes, the atmosphere does affect the brightness of objects we are looking at, because the atmosphere is very unstable. So when we usually do astronomy, we do it at places where the atmosphere is as stable as possible, so that is usually where it is as cold as possible and as dry as possible. So the larger the magnitude number, the fainter the star. This makes sense if you think of the bright star as first-class stars and the faintest visible stars as sixth-class stars. Ancient astronomers could only estimate magnitudes, but modern astronomers can measure the brightness of stars to high precision. So they've carefully redefined the magnitude scale. So if Hubble is moving and taking long exposure, so that's why Hubble can track objects. So we can point Hubble to different objects and we can make sure that it keeps looking at an object by making use of the orbit it is in, its own rotation, a few of its thrusters. So then you are still able to track the object and not get a blurry picture. So instead of saying that a star known by the charming name Chort is third magnitude, they can say its magnitude 3.34. Accurate measurements that show that some stars are actually brighter than magnitude 1, for example the famous star Vega, is so bright that its magnitude is 0.03. It's almost zero. A few are so bright that a modern magnitude scale must extend into negative numbers. On this scale, the famous star Sirius, the brightest star in the night sky for the southern hemisphere, has a magnitude of minus 1.46. Modern astronomers have had to extend the faint end of the magnitude scale as well. The faintest stars you can see with your unaided eyes are about 6 magnitude. But if you use a telescope, you will see stars much fainter. Astronomers must use magnitude numbers larger than 6 to describe such faint stars. These numbers are known as apparent visual magnitudes, and they describe the stars look to human eyes observing from Earth. So your interpretation of brightness is quite subjective, depending on both the physiology of human eyes and the psychology of perception. To be accurate, you should refer to flux, the amount of light entering that hits 1 square meter in 1 second. This makes a precise definition of brightness. A simple relationship connects apparent visual magnitudes and flux brightness. Are you guys all comfortable with the term flux? So does this only describe brightness in, yes, this is only for visual wavelengths. So yes, no, yes, no. Would you guys like me to explain flux a little bit better? Okay, so let me get my whiteboard out. So this definition of flux is the same everywhere. You get magnetic flux, electric flux. Flux is the same everywhere. So flux is defined if we have a area. So let's draw it from, let's see how pretty I can draw it. So if we have our area and we can draw these lines passing through it, that is defined as flux. So the more of these lines passing through our surface area, the higher our flux density will be. So if we draw it the other way around, so let's say this is our object. If our flux lines is perpendicular to it, then our flux density will be higher. But if we have something like this, and it's parallel to it and not perpendicular, then the flux density will be less. So what does the lines represent? So for visual light and telescopes, that represent the light rays hitting our telescope, so hitting our lens or mirror. In radio telescopes, that would be the radio waves, X-rays, gamma rays, infrared hitting the telescope. In electromagnetism, this can be our magnetic field lines or electric field lines, if you remember that from high school physics. So this is the short definition of what flux is. So if we go back to our slide, let me just get the correct slide. So for our purposes, we define flux as the amount of light energy that hits 1 square meter in 1 second. Does that clarify a little bit more? Cool. So in this way, modern astronomers can measure the brightness of stars to high precision while still making comparisons to observations and apparent visual magnitude that go back to the time of Hipparchus. So definition we should know, no, that's not a definition, no. So now this is a little bit, this is starting to become important. So if you struggle with this concept still after class, please contact me, then we can set up a Skype session, Zoom session, Google Meet session, any platform so I can help you. If you are able to come on campus, then we can even set up a consultation time in person as well. One thing for the class I would like you to remember, I have an open door policy. So if I'm on campus, you're more than welcome to come by my office anytime, and I will try to help you to the best of my abilities. I know with COVID, this has become a little bit more tricky, so you are more than welcome to contact me on any platform, as long as it is within reasonable hours. I know last year I had students sending me WhatsApp messages 1 o'clock, 2 o'clock in the morning to ask for help, but as long as it is within reasonable hours, then I will help you anytime. So, magnitude. So astronomers use a simple formula to convert between magnitudes and fluxes. So fluxes is brightness. So modern astronomers have defined the magnitude scale. So two stars that differ by 5 magnitudes has a flux ratio of exactly 100. So when are your reasonable hours? So reasonable hours will be anywhere from 9 o'clock the morning up to 8 o'clock the evening. Which part should I repeat? Okay, so let's do the slide again. So modern astronomers have defined the magnitude scale so that two stars that differ by 5 magnitudes have a flux ratio of exactly 100. So this is the key part of this definition. This is something you guys should know by heart. We're going to use this definition in this formula a lot of times for the rest of this module. So let me see if I can do this. So this part here is extremely important. So we have to know that if the magnitude of two stars differ by more than 5 magnitudes, or if it differs by 5 magnitudes, its reflux ratio will be exactly 100. Does that make sense? Yes, so you get formula sheets and the test. It all depends on how I'm feeling when I'm setting your test. So therefore, two stars that differ by 1 magnitude must have a flux ratio that equals the fifth root of 100. So I'm going to repeat this again. Therefore, two stars that differ by 1 magnitude must have a flux ratio that equals the fifth root of 100. And that is approximately 2.51 if you calculate it. Okay, are you guys still following what I'm saying? Okay, so with the next slide, we'll explain this a little bit more. Also, one thing I would also like to emphasize again that I said last week, I like this class to be as interactive as possible. I know with online classes that becomes a little bit tricky. So for everyone participating in tonight's class, I really appreciate it and thank you very much for participating. A deal I discussed last week of the class, I'm going to do now, is the end of the semester. When you need a percent or two, for example, to pass or a percent or two to get a distinction, I'm going to look at class participation. If you put that high class participation, then for me, I won't have a problem giving you a percent or two. But if you didn't participate in class, your attendance is low, then I might reconsider. Is that a deal for you guys? Okay, cool. So a few questions I see here is, so yes, if you look at FA over FB, that is the ratio. So magnitude doesn't have a symbol, it's just magnitude, yes. So if you go look at any course, if you describe magnitude, magnitude usually doesn't have a unit, but the symbol for magnitude, we have a parent magnitude. The symbol we will be using is MV. So what are FA and FB? Those are the apparent magnitudes of those stars. So this can be example magnitude 1, and that can be magnitude 5, because that's to be differed by 5, and that gives us a ratio of 100. So if we continue on to the next slide, we can see the magnitude difference of two stars. So the magnitude difference of, if you have two stars and their magnitude is both 0, then you can just read it off the table, is 0. If you have a magnitude difference of 1, that will be 2.51. A magnitude difference of 2, and continue on, magnitude difference of 5 is 100. Magnitude difference of 6 is 251, and so on and so forth. So is attendance taken for online lectures? I may take attendance for a few classes, but it won't count towards anything, because I know data is a problem and I know connectivity is a problem, and then there's load shedding. So I won't really look at attendance, but if anyone is in class, that's a big plus. So root 5 is just a historic definition that root 5 is selected. So now if we do an example, so just a heads up for you guys, the type of calculations we will do in our test and exam will be the same as our examples in the textbook. I will just change them up a little bit, but if you know how to do the examples in the textbook, you will know how to do the questions in the exam and quizzes and tests. So let's go through this example. Suppose star C is third magnitude and star D is ninth magnitude. What is their brightness ratio? So when are the quizzes? I will let you guys know when we are going to have a quiz. So the solution, the magnitude difference is 6 magnitudes, because we can see the one is third magnitude, the other one is ninth magnitude, so the difference between them is 6 magnitude. And if we go to the previous table, we can see 6 magnitude is corresponding flux ratio of 251. So therefore star C is 251 times brighter. So that means has 251 times as much flux arriving at Earth than star D. So a table is convenient, but for more precision, you can express the relationship as a simple formula. So we can go back. The flux ratio FA over FB is equal to 2.51 raised to the power of the magnitude difference. So we can do this calculation, say FA over FB equals 2.51. Going over the magnitude, so the magnitude here will be 6 magnitude. Someone's mic is unmuted. Is there a question? So is this how we should structure our answers? No, you don't have to structure your answers this way. I'm quickly going to see, we try and see whose mic is unmuted. So how do we get the magnitude difference? So right here in this example, the magnitude is given to us. So star C is third magnitude and star D is ninth magnitude. So it is as easy as going 9 minus 3. So if you plug this into the formula, then we will get our 251 again. Yes, magnitude difference of 6. Yes, and that's exactly the answer we are looking for. So if we do this calculation, we have 251.058. That's written horribly. So 9 and 3 is just the numbers that we got to solve for this textbook. So we have a star that's at magnitude 9 and we have a star that's at magnitude 3. So why do I get 250? That's correct. You just round it off to 251. So it looks like so 2. I didn't do the calculation myself. I was waiting for one of you guys to do it. But 0.58. Yeah, that's fine. So if you look at the calculation, it's just rounded. So you don't need to use to know the table, but you have to know this formula. If you know this formula, then you don't need to know the table. So let me also do the calculation quick. So this one is the correct answer. So rounding to 251, yes, that is justified. For astronomy purposes, that is justified. Okay, now a different example B. You can say 250 as well. 250 is also correct. It all depends on what is the accuracy you are looking for. Do you want to know the exact brightness of it, or the direct flux of it, or just something more approximate? So, second part of the example. If the magnitude difference is 6.32 magnitudes, what is the flux ratio? So solution, the flux ratio must be 2.51 to the power 6.32. So pocket calculator tells you the answer is 336. So the flux of the light from star A is 336 times larger than the flux from star B. So note that because the way magnitudes are defined, star A has the larger flux and numerically smaller magnitude. On the other hand, when you know the flux ratio and want to find a magnitude difference, it is convenient to rearrange the previous formula and write it as follows. The expression log means logarithm to base 10. So you guys all still following? Okay, cool. So question, how do we know the ratio? Give or in the table. So the ratio will be given in the question. So you have to. So where do we get this 2.51? The 2.51 was historically decided by astronomers. So if you go back a few slides. Modern astronomers has defined the magnitude scale as two stars that differ by 5 magnitudes of a flux ratio of exactly 100. So the fifth root of 100 is 2.51. Okay, everyone's still following? Okay, so let's do another example. So the light from Sirius has 24.2 times as much flux, so that means 24.2 times brighter than the light from Polaris. What is the magnitude difference? So solution, the magnitude difference is 2.5 times the logarithm of 24.2, which is written as 2.5 log 24.2. So you calculate, it tells you the logarithm of 24.2 is 1.384. So the magnitude difference is 2.5 times that, which equals 3.46. So if you write this, and in the equation form is we have so we want the magnitude difference is, so the magnitude difference, we can write this, use this formula. We can go MB minus MA equals 2.5 log FA over FB. Yes, that's exactly it. So 2.51 to the power as a difference. That's exactly it. So in this calculation, you can say 2.51. The example just rounded this one down to 2.5. So I know I've noticed this in the textbook. So if I were you guys, I would use 2.51. It is the most accurate definition. So everyone's still following? Okay. Okay, so before continuing on, are there anything you guys want to know, want to ask, want to take a breather of a minute? So where does the 2.5 comes from? The 2.5, we go back a few slides, comes from here. Modern astronomers have defined the magnitude scale as two stars that differ by 5 magnitudes. So it's the fifth root of 100 gives 2.51. So the 2.5 is supposed to be 2.51. It's just a little small mistake in the textbook. Okay, so the next part we're going to look at is the sky and its motions. So how do you guys imagine things moving around in the sky? So for this, we can consider using 2.51 everywhere. Yes, it is 24.2. If you plug everything into the equation, you will get the correct answer, because remember, we are using the logarithm of 24.2. So we can start looking at the celestial sphere. Ancient astronomers believed that the sky was a great sphere surrounding Earth, with stars struck on the inside like thumbtacks in a ceiling. Modern astronomers know that the stars are scattered through space at different distances, but it's still convenient to think of the sky as a great starry sphere enclosing Earth. So, the celestial sphere. The sky appears to rotate westward around Earth each day, but that is a consequence of the eastward rotation of the Earth. That rotation produces day and night. So notice how reference points on the celestial sphere, such as the zenith, nodal horizon, celestial equator, and north celestial pole and south celestial pole, define the four directions: north point, south point, east point, and west point. So here we have north, so let me get a pointer out. North celestial pole, south celestial pole, zenith, nadir. Astronomers measure, so let me rephrase this. So now we're going to start touching of how do we get distances to different objects in space. How do we determine distances of different stars? So do we have any website app where you can view, explore the universe in 360 degrees? Yes, there's a few cool apps. In the next lecture, I will show you a few of them. But in the meantime, if you want to explore for your computer itself, you can use Stellarium, which is a great app. And for your phone, you can use Google Skyview. So astronomers measure angular distances across the sky as angles and express them as degrees, arc minutes, and arc seconds. The same units are used to measure the angular diameter of an object. I know the math of arc minutes, arc seconds you're going to do in calculus this year as well, but this is how we calculate distances. So astronomers might say the star was 2 degrees off from the moon. Of course, the stars are much further away than the moon. But when you think of the celestial sphere and pretend that all celestial objects are attached to it, you can measure distance on the sky as an angle. The angular distance between two objects is the angle between the two lines extending from your eye to the two objects. Astronomers measure angles in degrees, arc minutes, that are 1/60th of a degree, and arc seconds, that is 1/60th of an arc minute. Using the term arc avoids confusion with minutes and seconds of time. The angular diameter of an object is the angular distance from one edge to the other. The sun and moon are each about half a degree in diameter, and the bowl of the Big Dipper is about 10 degrees wide. So these are definitions that you must take note of. So what you can see in the sky depends on your latitude. For example, if you lived in Australia, you could see many star asterisms and constellations invisible from North America, but you would never see the Big Dipper. So how many circumpolar constellations you see depend on where you are. Remember famous star Alpha Centauri? It is in the southern sky and is invisible from most of the United States. You can just glimpse it above the southern horizon if you're in Miami, Florida, but you can see it easily from Australia. So, the sky and its motion. So the goal of science is to understand nature and not to memorize definitions. So one thing that I know a lot of your other lecturers are not going to agree with me, but there's no point of memorizing definitions just because you can memorize definitions. If you want a definition of something, you can look it up in a textbook. It is much better to understand what it is. If you understand what it is, then you can explain to someone what it is, how it is, and then there's no need to memorize a definition. So the goal of science is to understand what's going on, not to create definitions of things going on around us. So a celestial sphere is an example of a scientific model. Many people, without thinking about it much, assume that the stars are not in the sky during the daytime. The stars are actually there day and night. They are just invisible during the day because the sky is lit up by the sun. Also, many people insist that famous star Polaris is the brightest star in the sky. It is actually the 50th visually brightest star. You now know that Polaris is important because of its position, not because of its brightness. In addition to causing the obvious daily motion of the sky, Earth's rotation conceals a very slow celestial motion that can be detected only over centuries. So now someone asked in the beginning of this lecture, constellations is changing, and that is where we are now touching on. So this is an important aspect of astronomy, and now a hint for your test and exams, you should be able to describe what precision is relating to astronomy. So in addition to causing the obvious daily motion of the sky, Earth's rotation is connected with a very slow celestial motion that can be detected only over centuries. More than 2,000 years ago, Hipparchus compared position of some stars with their positions recorded nearly 2 centuries previously and realized that the celestial poles and equator were slowly moving across the sky. Later, astronomers understood that this motion is caused by a top-like motion of Earth known as precision. So if you ever played with a gyroscope or top, you've seen how the spinning mass resists any sudden change in the direction of its axis of rotation. The more massive the top and the more rapidly it spins, the more it resists your efforts to twist out of position. You may recall that even the most rapidly spinning top slowly swings its axis around a circle. The weight of the top tends to make it tip over, and this combines with its rapid rotation to make its axis sweep out of the shape of a cone, and that motion is called precision. So if we look at a top on the left, the figure A, and Earth in figure B, we can see this is spinning upright, but this is spinning in a circular position or circular way. So that means when, let me get a drawing cursor out. So that means the top can be drawn that it looks this way, this way, this way, again this way, again this way. And where this axis is pointing is called precision. So is this similar to inertia? Not really. So should I explain this better, or does everyone understand what precision is? Okay, so to explain this further, so let me get a whiteboard out and see if I can explain this a little bit better. I will also share a video of this that will explain this a bit better. So we all remember I don't know if this is a bit before your time, but if you have a top, then you twist a rope around it and you spin it. It has a sharp point, and then it spins around in a circle. But while this top is, let me draw it again, spinning, it moves a little bit around on its own axis. So here we have our axis, but it spins around on its own axis. So the next moment, if we spin around on the axis, it will be a little bit more skewed. So here we can see our axis is now pointing this way. And then it can spin that it's upward again with axis going this way. And then it can spin to the other side again. And it looks this way again. So when we look from the top, we would see a circular motion this way. But if you look from the side, we will get this motion. Does that make sense? Okay, so let's go back to our slides. Okay, so we're back on our slides. So the question, is this the inspiration for the supposed doomsday theory where the Earth tips and becomes inverted? I'm not quite sure about that, but I will find out for you. So precession is the spinning motion of Earth that can only be observed over centuries. Yes. So this precession, so the spinning effect in a top that we spin on the ground, that happens in a few seconds. But this spinning motion where this motion is going around in this circle, that happens in centuries. So is the Earth spinning on its axis? Yes, the Earth is spinning on its axis. So Earth spins like a giant top, but it does not spin upright in its orbit. Its axis is tipped at 23.4 degrees from vertical. So Earth's largest mass and rapid rotation keeps its axis of rotation pointed toward a spot near the star Polaris. And the axis would remain pointed constantly in that direction except for the effect of precession. So over centuries, precession has significant effects. Egyptian records show 4,800 years ago, the North Celestial Pole was near the star Turban. The pole is now approaching Polaris and be closest to it in approximately the year 2100. In about 12,000 years, the pole will have moved to within 5 degrees of Vega. So figure 2.7c in our textbook shows the path followed by the North Celestial Pole. So next time you glance at the famous star Vega, remind yourself that it will someday be a very impressive North Star. So is the precession then measured relative to the tip of the top represented as an angle? So you can call it that way. So it's basically the, let me get the pencil out, this axis. So what is the cause of this type of motion? The cause of this type of motion is when Earth was formed. We will discuss that in later chapters. It's formed from a planetary disk where there's motion in the disk and our particles is clumped together. So how it's clumped together, that motion is retained, and that's how Earth kept its motion. So if we look at the night sky, how it's moving, our north celestial pole, or the axis of Earth, is right now on Polaris, and it will move through these different constellations. Here we will reach Vega. Then it will circle back to Turban in a couple of thousand years. And that, ladies and gentlemen, is chapter 2. Do I still have everyone's attention? Everyone's still following? Okay, so now in chapter 3, we're going to look at the cycles of the sun and the moon. So before continuing, what can you guys tell me about the cycles of the sun and moon? Through your life, what have you observed the sun and moon to do? So I don't think we're going to finish all the slides tonight. But if we don't finish, we will continue on in next week, Monday's class. So yes, the moon has phases. That gives us tides and seasons. First, I just have to check if the timetable has shifted. But so I will look after class and I will make an announcement on ClickUp. Okay, cool. Thanks for also have Monday's lecture on Thursday. Thank you. I will make that change in my diary as well. So the cycles of the sky are elegant and dramatic, and you can understand them fully if you know that Earth is a moving planet. Humans did not always know that. How we came to understand that Earth is a planet is the subject of the next chapter. Now it's only this week where on Thursday we are following a Monday timetable. So here we can see images of the sun and the phases of the moon. Question for you guys. In the image of the sun, the top left corner, what are those spots on the sun? Yes, and who can tell me what a sunspot is? Not solar flares. Yes, it's a part of the surface of the sun that's colder than the rest of the surface. And we're going to discuss sunspots in depth later on this module, but it is basically a cooler region on the sun. So Earth's rotation on its axis causes the cycle of day and night, but its motion around the sun, its orbit, that defines a year. Notice an important distinction. Rotation is the turning of a body on its axis. The turning of a body on its axis, but revolution means the motion of a body around a point outside. So annual motion of the sun. Earth's orbit is nearly perfect circle, but is shown in an inclined view in this diagram and consequently looks oval. Earth's motion around the sun makes the sun appear to move against the background of the stars. Earth's orbit is thus projected on the sky as a circular path of the sun, the ecliptic. If you could see the stars in the daytime, you would notice the sun crossing in front of the distant constellations as Earth moves along its orbit. So here we can see the annual motion of the sun. If we have the sun, we have Earth moving around the sun, and here we have different constellations. In March 1, the constellation Aquarius will be behind the sun. In January 1, Sagittarius will be around the sun. So that continues on throughout the year. The apparent path of the sun against the background of stars is called the ecliptic. If the sky were a great screen, the ecliptic would be the shadow cast by Earth's orbit. That is why the ecliptic can be described as the projection of Earth's orbit on the sky. Earth circles the Sun in 365.26 days, and consequently the Sun appears to circle the sky in the same period. That means the Sun traveling 360 degrees around the ecliptic in 365.26 days travel about 1% eastward in 24 hours, 1 degree eastward in 24 hours, about twice its angular diameter. You don't notice this apparent motion of the Sun because you can't see the stars in the daytime, but it does have an important consequence that you do notice the seasons. So Earth would not experience seasons if it rotated upright in its orbit, but it does have seasons because its axis of rotation is tipped at 23.4 degrees. From this perpendicular to its orbit, another way to say this is that Earth's equator is inclined at 23.4 degrees to its orbit. Because Earth's axis rotation is inclined at 23.4 degrees, the Sun moves into the northern sky and the spring and into the southern sky in fall. That causes a cycle of the seasons. Notice how the vernal equinox, the summer solstice, the autumnal equinox, and the winter solstice mark the beginning of the seasons. Earth's elliptical orbit is very nearly circular, and as it travels from perihelion to aphelion, its distance from the Sun varies only slightly and is not the cause of seasons. Earth goes through a cycle of seasons because of changes in the amount of solar energy that Earth's northern and southern hemispheres receive at different times of the year. Because of circular patterns in Earth's atmosphere, the northern and southern hemispheres are mostly isolated from each other and exchange little heat. When one hemisphere receives more solar energy than the other, it grows rapidly warmer. So, see a few questions. How do we have a leap year? Why does the Earth orbit the Sun for an extra day? Okay, so to describe leap year, so we can see, so when we do the calculations of leap year, so we define the definition of a year for the Sun to go from one point around its orbit. Let me get a whiteboard out. It will be explained a little bit better with a sketch. So one thing you guys should always remember is always use sketches to explain things. It helps a lot. So a year is defined. So let's draw the Sun. Here we draw Earth. And this is our orbit around the Sun. So 1 year is defined for Earth to go around the Sun and reach the exact same point. So when we do this, we have seen the orbit takes more or less 365.26. Who is drawing on my whiteboard? So if we draw this, it comes to 365.26 days. But depending on what's happening with the Sun's activity and what's happening in our solar system, from year to year, this can be a little bit longer. For example, this can be 0.34, and in other years this can be even shorter. For example, it can be 1.1. So generally this is rounded to 2.6. But also to remember is Earth's rotation will over millions and millions of years slow down. But to keep the point of orbit around the sun constant, to keep the definition the same, we add leap years. So add an extra day to compensate for the rotation that's being lost, and that's how we have a leap year. Does that make sense to you guys? Do you know about a leap second? Yes, a leap second is exactly the same thing as a leap year. So every now and then a leap second is added to keep the exact point from orbit from the Earth around the Sun exactly the same to the same place. And you guys are all familiar of how seasons work. Yes, I see you have raised your hand, Miss Niemand.
Sorry, so you were saying that now I've lost my train of thought. Okay, never mind, sorry.
No problem. If you remember your question, you're more than welcome to ask. So leap explanation second is exact same for a leap year. So when we are moving around the sun, we define the Earth from exact point around the sun, moves around the orbit to the same point as 1 year. Now, because the rotation of Earth is slowing down, to keep that point the same, we sometimes add leap seconds and we sometimes add leap days to keep that point constant so we can keep the definition of a year. Pleasure. So are you all comfortable with how seasons work? So, I can see. So you say that Earth is rotating slower. Does that mean that the year will become longer? So right now that slowing down will happen only in millions and millions of years. So eventually, yes, it will become longer because we can't continue by adding leap seconds or leap years. So in some point in history, we will have to redefine a year or redefine a day. But for now, for all intents and purposes, adding a leap second and a leap day solves the problem. So is the speed at which the Earth revolves around the Sun also slowing down? Currently, the speed is constant for orbiting around the Sun. So does the Sun experience weather? Not weather as we know on Earth. Sun has, we call it different kind of weathers. The surface of the Sun can be a little bit more active. So then we will see more solar flares from the Sun. And at some stages, and it will be less active, so that means also less sunspots, and that is how we define the weather on the Sun. So does the slowing down also happen to other planets? Yes, it also happens to other planets. So remember, in space, it is not a... So usually when you think about textbook problems, usually you think about physics. In some questions, it would say you can ignore friction. You can ignore wind resistance. But in actual life, we can't ignore those, I'm going to say, features. So eventually the rotation speed of different planets will start slowing down. So no, they will not stop moving because the energy are too high. They will just become lower, 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 and lower. So what is causing this friction in space? Not friction in space, but you can think about angular momentum. So if you look at Newton's laws, angular momentum, you only have X amount of angular momentum while it's spinning. That angular momentum is transferred into other energies as well. And that's why everything slows down. So if you look at this image, we can here see how the Earth is moving around. So for example, while it's tinted, we can here see where the celestial equator is, winter solace, ecliptic, vernal equinox, summer solace, and northern celestial pole. Does the shape of a galaxy get affected when everything slows down? Yes. We will discuss that in this module as well. So here we can see the Earth as it is canted at 23.4 degrees. The one hemisphere gets more light. So right now in this image, the northern hemisphere receives more light than the southern hemisphere, and that's why it's summer. So here it's the other way around. The southern hemisphere receives more light than the northern hemisphere, and that's why we have summer and winter going around the sun. Okay, so I think we're going to continue with the motion of planets in Thursday's lecture. So I think we're going to call this a night. If you have more questions, I will remain active for a few more minutes. Otherwise, you guys are more than welcome to log off. Have a great evening. Good luck with the rest of your modules for the rest of the week, and I'll see you all on Thursday. So question, why are places closer to the equator hotter? Because on the equator, let me get this pointer out, there's not much difference between the fast north side and far side, so it gets constant radiation from the sun throughout the year, and that's why it's hotter. So how does the sun move through space? So the sun rotates around its own axis, but it also moves through space. So in space, it orbits around the center of our own galaxy. All planets are tilted, but all planets doesn't have the same tilt. So if you have a tilt of basically 1 or 2 degrees, then you won't really have seasons. But the bigger the tilt is, the more extreme your seasons will be. So how likely is it going to see, so I mean the ISS passing over? So the ISS moves over South Africa quite a few times a month. I will post a notification for you guys to be able to see it. So no problem for drawing on a whiteboard. This is a learning curve for all of us working with online lectures. So do we move along with the sun? Yes, we move along with the sun. It's a pleasure. So I'm going to stop recording the session.